Now we're going to show how the method works out with our familiar y double prime minus y prime, and that's wrong. Okay, I've corrected that. It's y double prime minus y equals tangent t. y1 equals e to the t, y2 equals e to the negative t are the solutions to our characteristic equation, to the homogeneous equation. So we move immediately to this determinant, y1, y2, y1 prime, y2 prime. And that, not determinant, to the matrix, y1, y2, y1 prime, y2 prime. And that equals e to the t, e to the negative t, and y1 prime being the derivative of e to the t is e to the t, y2 prime being the derivative of e to the negative t is negative e to the negative t. So here's our matrix y1, y2, y1 prime, y2 prime. Now the determinant of the matrix is what? It's just this times this. E to the t times e to the negative t is 1. Of course, with the negative here, we get a negative 1. And the other diagonal multiplies out to plus 1, but of course we subtract it, so we get negative 1 minus 1, and that equals negative 2. So the determinant of our matrix is negative 2. The inverse of our matrix is then going to be 1 over our determinant times the matrix we get when we switch y1 with y2 prime, and then leave these where they are but make them both negative. And the significance of this is our particular solution is yp equals u1 y1 plus u2 y2. Our matrix, I'm debating whether to write the matrix equation down or just write the result. Okay, sorry for that little delay, but I've decided. Our matrix equation is y1, y2, y1 prime, y2 prime times the vector u1 prime, u2 prime equals 0 g, g being the non-homogeneous term on the right-hand side. In this case, g is going to be the tangent of t. So our solution then is u1 prime, u2 prime equals y1, y2, y1 prime, y2 prime inverse multiplied by 0g. And what's the inverse of this matrix? Well, it's here. Now I should have gone ahead and written it out up here. y2 prime, remember that y2 is our negative e to the negative t, or is our e to the negative t, so its derivative is negative e to the negative t. And negative y2 is negative e to the negative t. I don't think I wrote my negative down here. I hope you caught that. I didn't. And our negative y1 prime is going to be the negative of the derivative e to the t, so that's negative e to the t. And y1 is just e to the t. Now we write out this solution. U1 prime, U2 prime is going to equal the inverse matrix, which is negative 1/2 multiplied by negative e to the t, e to the negative t, and negative e to the negative t, and negative e to the t, e to the t, multiplied by the matrix 0g. As I pointed out, g is the tangent of t, so we have 0 tangent of t. The product then is, if we multiply the row by the column, we get negative e to the negative t tangent t. That's multiplied by the negative 1/2. So we have 1/2 e to the t tangent of t. And then we multiply the second row by the column, we get a negative 1/2 e to the t tangent t. I'm pretty much out of room, and we are going to go on with this in another clip that I'll start with a fresh piece of paper, but I'll write down here that now U1 prime is then 1/2 e to the t tangent of t, and U2 prime is negative 1/2 e to the t tangent of t. If we can integrate these two functions to find U1 and U2, because of course what we have here is U1 prime and U2 prime, we will then have a function U1 and a function U2 that we can substitute here, along with Y1 and Y2, which are just e to the t and e to the negative t, to get our particular solution. So the method simply comes down now to integration. And I'll point out finally that anytime we have a fundamental set for our homogeneous equation, this method will lead us to equations for U1 prime, or expressions for U1 prime and U2 prime. You might be wondering how we're going to integrate these things. So am I. But if we can then integrate these, we will have what we need to build a solution. So the method is actually very mechanical once you get used to it. And it always, again, leads you to a couple of functions that you have to integrate in order to get a final solution. In the preceding, we saw how the matrix equation shown here has solution, and we worked out some of the details of that solution. Now this matrix equation is a solution for U1 prime and U2 prime of a non-homogeneous second order equation. And applying this solution to the equation y double prime minus y equals tangent of t, we simply follow the method of this solution to obtain the solution for U1 prime, U2 prime of the equation y double prime minus y equals tangent of t. In so doing, we end up in a very straightforward manner, once you get used to the operations, with equations for U1 prime and U2 prime. Now there was one mistake here, and I'm going to go ahead and correct it now. There should be an e to the negative t on the first element in this column vector, and there should be a negative on the t and the U1 prime, because of course multiplying this row by this column, it's negative e to the negative t that's multiplied by tangent t, and we're going to get the e to the negative t out of that. And in doing that, I see that, don't know what I did, but or why I did it, but I did reverse the sign, so that the negative e to the negative t, I'm sorry, the 1/2 is negative, so this should have been positive. This is negative, not positive. And the solution is as I've rewritten it with the negative t here.